Today we are speaking to Semih on the role of feedback alignment in self-distillation, a paper recently published, and I believe it's been accepted into the ICML conference for presentation. Is that right, Semih?
Yep, that's correct.
Fantastic! Congratulations on that. Why don't you
Thank you.
why don't you kick us off and give us a bit of a description of what you were working on when you put this paper together?
Right. So the paper, I would say, has two main components, like two main perspectives. One is, as the name suggests, self-distillation. That's like one major topic. And then the second is um, how does the role of how agents communicate play a role in self distillation. So I can start with, I guess, going over very briefly what self distillation is, so that the rest of it makes sense.
Absolutely. So we've spoken about distillation a few times up here, basically training. Correct me if I'm wrong. Training models off previous models, and in the end, they end up smaller and more efficient in a way.
In this, yeah. In a sense, yeah. Like it goes back to what you said. Can It's like the, I guess, more broad area of general like distillation. And then it has been narrowed down a couple of times and ended up with self distillation. And I think that like process of narrowing down is like quite illuminating to understand what self distillation is. So I think, yeah, that's like a good starting point. Now distillation is there's this 2015 paper by Geoffrey Hinton, who I think like that paper was the one that made it this idea popular. So overall, like what we are trying to do is, we have two distributions, right? Like I don't want to go into like the mathematical details, but I think like without at least mentioning like distributions, like probability distributions, it becomes like extremely difficult to explain what we're doing. So I will try to keep it at the very surface though.
Go for it. And you can be as detailed and complicated as you like. I'm sure I'll manage to keep up.
Thank you. Yeah. So there is this probability distribution that is good. That we aspire to be. So that's the teacher, and we are trying to be more like it. That's what like that's the goal of distillation. So what distillation is doing is like it's receiving data points from this teacher, and then fitting its parameters, changing its parameters to fit to that data. And then I hope I'm not skipping anything in between, but there was this notion of on policy distillation. So as I've said, in original distillation, we get the samples from the teacher, but that creates some instability or like difficulties when we are producing, like when we are doing inference. So let's say that you are a physics expert and I don't know anything, right? And you give me some like high level information about physics, like very challenging topics, and then when it is time for me to generate that information, like pass that information to other people, like either I have to like either they have to ask me about exactly what you have taught me, or otherwise like I'm not going to be able to, like, that's not in my expertise to kind of like connect the dots And if they ask me about something else, like I only know about what you taught me.
Right.
So in a sense, on-policy distillation addresses that. So in on-policy distillation, we generate the data, and then we get the distribution from the teacher for that data that we have generated. So it's kind of like going to the teacher and saying like, "Hey, look, I did this," and then the teacher's telling you that like, "Don't do that. Do this instead." So you're getting kind of like guided,
Hmm.
feedback on like what you are able to produce.
You're getting corrected and directed a little bit.
Exactly. Exactly. Now, this still though requires us to have like the distribution of the teacher. So self-distillation goes one level beyond,
Hmm.
and it gets rid of that necessity. And now we just take textual feedback from or any kind of context, external context. This can be again like a textual feedback from the teacher from like a stronger model, and then we put that information into our context. So now we have the original distribution that we generated the response with, right? With
Hmm.
just like only the problem. And then we have another distribution where we have the problem and the textual feedback from the teacher in context. So these are two different distributions that depends on our parameters. Like it's just like what the same model, but the prompt changes. And self-distillation distills that um, distribution with additional context to the one without the context, so that the model acts as if it has that additional context at inference time, even though it hasn't. Does
Hmm.
that make sense?
I think so. The the self distillation element, the self, it's somehow not requiring a teacher in the older sense of the setup.
Exactly, exactly. Yeah. So that's the difference between, well, it doesn't require us to have access to the
Hmm.
probability distribution of the teacher.
Okay.
So still, we can make use of a stronger teacher model to give us like textual feedback, like giving us guidance on what the model should have, like how it should have responded. But we don't need the full probability distribution anymore.
Okay. Okay. Great. That's obviously got some very large, I guess, efficiencies and um, savings in effort and resources in order to do that.
Yeah, and I guess a good example is, like when you're chatting with Claude or ChatGPT, whatever,
Hmm.
you don't see the distribution that generated the response, right? You just get the
Right.
response. So self-distillation works in this case, whereas we cannot do any kind of other distillation to learn from our chat with these frontier models, because they don't expose the distributions.
Okay. Fantastic. Now, so where did you go next?
Right. So given this like technique, which has been getting quite popular for post training, like fine tuning of language models.
Hmm.
Um, the thing that um, differs the two distributions is the additional context, right? Like for like one, the original distribution is our model given the problem, and then the distribution that we want to have is our model given the problem plus additional context. So that additional context is the only difference, and therefore it affects like that context affects everything, like
Right.
and while implementing this like self-distillation training, it just like some point, very early in the process, you ask like, how should these models talk to each other? Like I have one, let's say, small model and one large model. Like how should the large model be talking to the small model? It's just like a very, very basic design parameter that pops up like, at the first stage of implementation. And turns out that like style of communication matters a lot. So what we did in this paper was discovering what form of communication, what style of communication works best for self-distillation. And yeah, we compared three forms of styles. One is, just like, one is actually binary correctness signal. So the model gets to learn whether the answer, the response that it gave is correct or not.
Right.
That ends up being, GRPO training that has been widely implemented, adopted since I think 2024. But yeah. And the second one is what had been done in previous literature, which is sharing the entire reference solution that comes with the data set to the smaller model, with the smaller model. Now, this like reference solution is a correct solution that has been generated by a strong model at some point, and it is saved with the data set and shared. It comes with the data set. So we give that as the additional context to the small model. And then the third one that, we proposed was giving step-by-step aligned feedback to the small model on its answer. And we found that this like step-by-step aligned feedback works best as the communication method. So if you have like agents giving response to each other, trying to improve each other, we have found that this like curated response of like agentic communication works best.
So instead of effectively giving the answer for a model to work towards, you're guiding it as it goes along on the right path, more like a tutor,
Exactly.
more like a tutor than a teacher.
Exactly. That was going to be the exact analogy that I was going to use.
Sorry,
So let's say
stole it from you.
So let's say that you have you take an exam, and your exam is graded. The teacher returns it back to you. Now there are like three forms of signal that you can get from that marks. Like either like, let's say the teacher like puts a huge check or a cross on your answer. So that's like the first one that I had mentioned is like the binary correctness signal.
Right.
The second one is, you get like a cross or a check, and then the teacher tells you to look at the the reference, the exam solution reference, right? So you go there and like you see like, oh, this is the way that I could have solved it. And then the third one is, you again either get a cross or a check, and then the teacher tells you like, you did everything up to this step correctly, but then you should have continued on like this. So it turns out that, like I personally would learn most from the third one because it aligns with what I'm already inclined towards producing, right? I don't have to realign my solution strategy. This is already what I'm like, what I tend to solve the problem using, like this methodology. So it turns out that like the model doesn't have to do like larger updates, learning a new surface form, like a new style of solving. But if you implement this step-by-step aligned feedback approach. So it turns out that like the models learn pretty similarly to, I think, what most students would, given that they are able to solve up to a certain point. You know, they have some certain capability, but not like, they're not as good as a teacher.
Absolutely, there certainly are a lot of parallels with human learning and teaching, in the sense that the third method you're describing, the method you've written about, is in a way reinforcing and encouraging what someone is getting right, but then pushing them to go further in the right direction.
Exactly. Yeah. Yeah. And another cool thing that we have done in this paper is like having a mechanistic interpretability like argument for, you know, why this is so, like why we're seeing this. And you know, when I say mechanistic interpretability, is it means like we know some stuff about like how these language models work. So using that knowledge, you know, like can we explain this phenomena that we are seeing? You know, so one of those things that we know about language models is induction head copying. So it says that if a model sees something like a sequence, let's say A and then B in its context, then when it sees A, when it generates A in its response, it is very likely to generate B afterwards. So whatever it sees in its context, if it generates one the prefix for that, it is likely to continue with what it had seen in its context. And we use this observation to, you know, like it's an explanation of why this helps when we tell the student that, oh, you have done, like this is what you have done until this point and this was good. Like having that in this context reinforces by this induction copying hypothesis, you know, producing that exact starting point. But then we switch to what it could have done, and that distills that new information into the original weights, if that makes sense.
Okay. Yes, absolutely. In the thread that you posted on X, you referenced multi-agent LLM systems being everywhere, all the agents beginning to talk to each other, critiquing each other, giving feedback, etc. Effectively, what you've been describing in that the various methods of teaching. Under that multi-agent system that we're moving into all over the place, how do you see this? Where do you see this work fitting, and how do you see it affecting these systems as we go forward?
Yeah, so it is becoming quite the you know, multi-agent workflows is becoming quite the dominant approach for improving inference quality nowadays. You know, I've been seeing it a lot around like every major chatbot implements it. You know, the like Claude Code does it, Cursor. So like this, like agentic multi-agent workflows is, I mean, it has already been, I think, it has already become one of the primary implementations, one of the primary techniques.
For sure.
And
I get annoyed when Codex forgets to spin up extra agents.
exactly, yeah, you always see, yeah, like Cloud Code, Codex, like they all, call sub agents, and then they return something to the orchestrator. The orchestrator decides on that, blah blah blah. And I like briefly mentioned, but that was kind of like the starting point of this research too. Like I was implementing something like that, you know, like a multi-agent workflow, and then when it came time to decide on how the agents should communicate to each other, you know, like I gotta write the prompt, right? I gotta specify how these agents should give feedback to each other, respond to each other's, whatever they return in this workflow. So that, literally that architecture is what made this, what started this research. The need to specify what works best, and what kind of feedback works best in these multi-agent workflows. And what was I going to say? Since these systems are becoming more prevalent, also the data that they generate is becoming quite, they're becoming the predominant type of data that we will have at some point. So it's all going to be agentic communication, like terabytes and terabytes of them giving feedback to each other and, their chat with each other. So when it is time to train using this data, self-distillation will be one of the methods, that we use for training. And our work says that to have the best training results, agents should be communicating in a step-by-step aligned way. For the training process to be optimized.
That's a very interesting thing that I don't think about very often, but all of the, as you said, the discussion between the agents is actually going to be saved data somewhere and just build this huge pool. So improving the quality of that effectively is one advantage of what you're doing.
Yep. Yeah. Just like, how we use chatbots, we give them like feedback on what we would have preferred.
Yes.
Like the agentic systems, also do that. And, for them to not make the same mistake again and again and again, or needing to have that feedback in the prompt all the time, at some point they need to bake this information into their weights.
Right.
And yep. So this is, I think, it will become like saving that data and then training on that data is going to be quite widespread.
Fantastic. There's one last piece as I was reading through your blog. It wasn't only the there was a piece you wrote, sorry, about the connection to the process supervision, working through the individual steps and the step level rewards. Can you just go into that a little bit further for me?
Yeah. So process supervision is essentially figuring out what parts of the response of a model were good and what parts are bad. So there's something called a process reward modeling. That it is training reward models specifically for this job. So these are like trained models, and they eat up high quality data, labeling what part of the solution was good, what part was bad, so on and so forth. And this allows the models to learn in the way that I have explained. They get feedback on what was correct and what was not, rather than getting like a binary signal over all of their reasoning trays as to whether it was correct or not, or getting like a entirely different surface form like solution. So this process supervision is what is essentially the thing that makes it possible to say like this part was good, this part was bad. And like I said, process supervision requires training of these reward models. And we have shown that in this work, if you do self-distillation with step-aligned feedback, the way that we propose, that amounts to process supervision, but you don't need to train a reward model. Like, your model is already able to convert that like textual feedback from any strong enough model that is, not like a specifically a process reward model. It can be like any strong model giving you textual feedback. It can turn that information into process supervision through self-distillation. So you sidestep this difficult, costly process of training a reward model.
Absolutely fantastic. I can see the shortcuts and the benefits. Not shortcuts, is the wrong word, but the efficiencies and the benefits of this absolutely immediately. And I also love the idea that the research idea actually began because you were sitting there trying to figure out how to write the right prompt. You're out there solving real world problems.
yeah, exactly. Yeah, it's a very we also like got some reviews, feedback when we submitted the paper, and one of the reviews was saying this is actually like quite enlightening in terms of like application. It shows you it has a good like application implication.
Definitely. I think that's quite clear. Well, thank you so much, Semih, for coming on and joining us. Is there anything you'd like to leave the people listening with before we wrap up?
No, I think all of what I've said like sums it up quite comprehensively. I do believe that as we have been seeing, like multi-agent systems, their decentralized implementation, it's gonna get more and more widespread. And I hope that our technique will shed light on, how the communication style in these systems should look like.
Definitely some very important work that you've been doing, I think. Well, thank you again. Thank you everybody for coming along and listening. If you want to read a bit more, I've got a couple of links at the top of the space for the Gensyn blog and also Semih's thread. That'll take you through to the Arxiv paper as well. And if you happen to be at ICML next month, make sure you drop by and say hi to some Gensyn team members who'll be out there as well. Thanks, everybody.
Thank you.